All right. So the next way to assess variable importance that we'll discuss is called Olden's method. And this is, so it's named after its creator. Um, and this method involves kind of tracing through the weights associated with a particular independent variable and kind of adding them up in a sense. Okay. And so to understand how this method works, I have a much simpler neural network being displayed here. Okay, so this is a neural network with only two independent variables and one hidden layer, and this hidden layer contains three neurons. Okay, and let's assume that after I've gone ahead and I've fit my artificial neural network, that I get weights for each of these connections that look like this. Okay, and you can see here I'm actually only showing you the weights related to the bedrooms variable, okay, because I want to imagine that we're trying to compute the importance of the bedrooms variable. Okay, so you can see this bedroom variable is connected to the three neurons in the hidden layer with weights 1.5, minus 0.7, and minus 0.5, and then subsequently those neurons are connected to the output layer with these weights that I've shown here. And I've also written these weights again in this table. Okay, so so then let's consider, what is sort of the net impact of this bedroom variable on our output layer. The only way that the bedroom variable can directly affect our final predicted price is through the weights that I've shown here. Okay, and so consider. So this neuron up here, this first neuron in our hidden layer, has a positive weight with respect to our output layer. Okay, so this weight is positive. So what that means is that, whatever number gets passed into this neuron, okay, that number is going to be multiplied by 0.3, and that's going to go towards getting the output of our final neuron here. Okay, and so in other words, what I'm saying is that this neuron here has a positive effect on the price. If the value that this neuron was spitting out were to go up, then our predicted price would also go up. Okay, and notice that this bedroom neuron has a positive effect on this intermediate neuron. And so basically that means that if the value of bedrooms were to go up, then the value of this neuron would also go up because we're multiplying by 1.5. And then if the value of this neuron goes up, then the value of our final price is also going to go up. Okay, so since both of these numbers here, both of these weights are positive, what we're saying is that through that channel at least, bedrooms is going to have a positive effect on price. Okay, on the other hand, consider this one. Okay, so this intermediate neuron, just like the first one, okay, this second neuron in our hidden layer, also has a positive effect on our final price. In fact, its weight is even a little bit higher. However, bedrooms has a negative effect on this middle neuron here. So the higher the value of bedrooms, the more bedrooms we have, the lower is going to be the value spit out by this intermediate neuron, because this bedroom neuron is inhibiting this intermediate neuron here. And this neuron then goes on to have a subsequent effect on price. So in other words, because this weight here is negative, okay, that's showing that basically this channel from this neuron to this neuron to this neuron ends up having a negative effect on the total price. Okay, and then finally, let's consider this final neuron here, okay, this third neuron in our hidden layer. So this neuron has a negative effect on the price. You can see it's the weight here is minus 0.6. But then bedrooms has a negative effect on this neuron. So what is the total effect of bedrooms on price then through this channel? Well, this is kind of like a double negative, right? This neuron, bedrooms, is inhibiting another neuron that has a negative effect on price. So if you inhibit something with a negative effect, well, then you're creating a positive effect. Okay, and so you can see basically it's almost like what we need to do is multiply these signs. Okay, a positive and a positive creates a net positive effect. A negative and a positive creates a net negative effect. But then two negatives goes back and creates a positive effect. Okay, and so actually what Olden proposed is to simply do exactly as I just said. Take each of these weights, multiply them, and then add the results. Okay, so you can see here I multiplied 1.3 and 0.3 and got 0.45. I multiplied this negative 0.7, this positive 0.5, and I got negative 0.35. And then I finally took these last two and I multiplied them as well. Finally, I added all of these numbers up to get 0.2. Okay, and so the final metric for this particular variable for bedrooms, according to Olden's method, would be 0.2. This is like 0.2 would be sort of the importance of bedrooms according to Olden's method. And then what we would simply do to compute the importance of another neuron, like lot size, is to simply repeat this process, but to use the weights associated with lot size. Okay, so I hope that makes sense. It's basically what we're going through is we're going through and we're tracing the connections between our independent variable of interest and our final dependent variable, and we're sort of successively multiplying the weights and we're summing them. Okay. Okay, so let's go back to R and see how this is implemented. Okay, and luckily for this particular function, there is a package for doing it. Okay, and the package for doing it, this Olden command, is contained in this package neural net tools. Okay, so I'm going to go ahead and I'm going to run this Olden. Okay, and you can see here is our result. And let me see if I can make this a little bit bigger for you. Make it a little wider here. Okay, so so you can see that so these are importances, okay, according to this metric, okay, and by this metric, the single most important variable appears to be land value, followed by age, followed by being on the waterfront, okay, and you can see this new construction variable is being rated as very unimportant according to our metric. Exactly why this particular variable was rated as so unimportant compared to some of the other ones, I'm actually not 100% sure. Okay, I'm gonna look into this a little bit. Okay, but I did sort of check the code. This isn't a bug or anything like that. It just thinks that this variable is indeed very unimportant. Okay, exactly why that is, like I said, I'm not 100% sure at this point. Okay. Okay, so then our final method is once again going to be looking at the partial effect of a given variable. So as you'll recall, these partial dependence plots, what they do is they simply say, well, okay, if I want to understand what the effect is of a given x variable, say the number of bedrooms, on my y variable, okay, well, why don't I simply try to predict the value of the y variable while changing the number of bedrooms, the x variable in question, okay? So imagine going to our data, in our data we have, the number of bedrooms takes on all sorts of different values, okay? But imagine that I set all of those houses to have just a bedroom value of 1. And then I predict what the home price would be for all of our houses, and I take an average of that. Then suppose I increase the number of bedrooms to 2. Once again, I predict the values of all the houses, I take the average, and then I record that number. Okay, and if I do this for the whole range of possible bedroom values, let's say between 1 and 9 bedrooms, well, and then I plot each one of those data points, okay, then I would come up with this partial dependence plot for the number of bedrooms. Okay, now the command to do this, actually we can use the same command that we've been using before, which is this partial command. Okay, so you can see here I'm calling partial on the neural network that we just trained. I'm saying, let's use test as the prediction data. Okay, I'm telling it the predicted number, I'm sorry, I'm telling it that bedrooms is the variable that I want to examine, okay? This type regression here, so right now we're using our neural network in regression mode because our dependent variable price is a continuous variable, okay? And then finally, plot equals true. If you don't put plot equals true here, it'll give you a table. But right now, I'm interested in looking at the plot. Okay, so let me go ahead and run this. Okay, and you can see here that it predicts that that the price here is going down as the number of bedrooms diminishes. Okay. Now, you'll note that it's a little bit messed up here in terms of the axis. You can see the number of bedrooms is going from 0 to 1, and the y hat is going from 0.3 to 0.24. Now, that's just because, remember, that these variables have been normalized. These variables have been scaled, so they're all between 0 and 1. So this 1 here doesn't mean that the house is 1 bedroom. It just means this 1 represents the maximum value of bedrooms that we observed in our data, which I think was 9. Okay, and again, this 0 represents the minimum value of bedrooms, which presumably would be a 1. Okay, and so you can see here that the neural network is actually saying that as the number of bedrooms increases, it seems that the price actually decreases in our data set. This was something that we were finding with the random forest as well. Okay, so just to recap then, so those are the 3 ways that we can assess variable importance using artificial neural networks. There's this idea of assessing importance by omission, scrambling a variable, and then looking at how the accuracy changes. There's this Olden's method that we just discussed, and there's this method that involves simply looking at the partial effects. Okay. Okay, so in the final video, I'll talk briefly about your homework assignment. I'm actually going to give you the assignment for the whole week today. Okay, so you guys have the whole week to work on it because on Thursday, we're primarily going to discuss the project.